Welcome to video lecture. Myself Ashwini RK, Assistant Professor, Civil Department, Rovni College of Engineering and Technology. Today we are going to see about the properties of fluid. First, a small introduction about fluid mechanics. Fluid mechanics is a branch of science which deals with the behavior of fluid at rest as well as in motion. The fluid mechanics is divided into three parts: fluid statics, fluid kinematics, and fluid dynamics. Fluid statics is a study of fluid at rest. Fluid kinematics is a study of fluid in motion where pressure forces are not considered. Fluid dynamics is a study of fluid in motion where the pressure forces are considered. Properties of fluids. Density. Density or mass density of a fluid is defined as the ratio of mass of the fluid to its volume. The density is denoted by the symbol ρ, that is equal to mass of the fluid by volume of the fluid. Specific weight or weight density. Specific weight of a fluid is the ratio between the weight of the fluid to its volume. Here, the specific weight is denoted by the symbol small w. That is equal to weight of the fluid divided by volume of the fluid. Specific volume. Specific volume of the fluid is defined as the volume occupied by unit mass of the fluid. Specific volume is equal to volume of the fluid divided by mass of the fluid. Specific gravity. Specific gravity is defined as the ratio of density of the fluid to the density of standard fluid. Specific gravity is denoted by capital S, that is equal to density of liquid divided by density of water. The standard liquid is water and for gas it is air. Viscosity. Viscosity is defined as the property of the fluid which offers resistance to the movement of one layer of fluid over another layer of the fluid. So, we have considered two layers of the fluid at a distance dy apart with a velocity of capital U and U plus du. Viscosity together with relative viscosity causes shear stress acting between the fluid layers. Shear stress is proportional to the rate of change of velocity with respect to y. That is, tau is directly proportional to du by dy. So, in order to remove the proportionality, we are including tau is equal to mu into du by dy. Here, the mu is the coefficient of dynamic viscosity. Viscosity is also defined as the shear stress required to produce unit rate of shear strain. So, the unit of viscosity is Newton second per meter square. Newton's law of viscosity. It states that the shear stress tau of a fluid element layer is directly proportional to the rate of shear strain. Kinematic viscosity. Kinematic viscosity is defined as the ratio between the dynamic viscosity and the density of the fluid. The unit of kinematic viscosity in SI system is meter square per second and in CGS system it is centimeter square per second or Stokes. Types of fluid. Here the fluids are categorized into ideal fluid, real fluid, Newtonian fluid and non-Newtonian fluid. Effect of temperature on viscosity. The viscosity decreases with increase in temperature of a liquid. Viscous forces, cohesive forces, molecular momentum transfers. In liquid, the cohesive forces dominate due to closely packed molecules, and with increase in temperature, the cohesive forces decreases and hence decreasing the viscosity. Next property, surface tension. Surface tension is defined as the tensile force acting on the surface of the liquid in contact with gas or on the surface between two immiscible liquids. So, the surface tension on a liquid droplet is given by capital P is equal to 4 sigma by d. Surface tension on hollow bubble, capital P is equal to 8 sigma by small d. Surface tension on liquid jet, P is equal to sigma into 2L divided by L into d, where in capital P represents the pressure in Newton per meter square, sigma represents the surface tension in Newton per meter, small d represents the diameter of liquid droplet, capital L represents the length of water jet. The next property, capillarity. Capillarity is defined as the phenomenon of rise or fall of a liquid surface in a small tube relative to the adjacent general level of liquid where the tube is held vertically in the liquid. Here, the rise of liquid in the tube is known as the capillary rise, and fall of liquid in the tube is known as capillary depression. The factors affecting the rise or fall depends on density of liquid, diameter of the tube, surface tension of the liquid. So the expressions of capillary rise. Under state of equilibrium, weight of the liquid of height is balanced by the force at the surface of the liquid in the tube, where the weight of the liquid is equal to density into acceleration due to gravity into area of the tube into h. Vertical component of the tensile force is equal to sigma into pi d into cos theta. Equating the above two equations, the capillary rise is given as h is equal to 4 sigma cos theta by rho g d. If the theta is equal to 0 for clean water and glass tube, h is equal to 4 sigma by rho g d, where rho is the density, sigma is the surface tension, and d is the diameter of the tube. Expression for capillary depression. If the glass tube is dipped in mercury, the level of mercury in the tube is lower than the general level of the outside liquid. So the capillary depression is given by h is equal to minus 4 sigma cos theta by rho g d. Here the theta is equal to 128 degree for mercury and the glass tube, and where rho represents the density, sigma is equal to surface tension, and d is the diameter of the tube. Thank you.